In our previous video, we talked about sampling error and bias, and we said that bias was a bad study design, and sampling error was error that just occurs naturally when we take a sample, because the sample is only a subset of the population. Specifically, we said that a bad design or bad execution produced biased data, and nothing could fix that. We said with sampling error, we could reduce it, not eliminate it, but we could reduce it by increasing sample size. And we basically said sampling error occurred because we're taking a small subset or a microcosm of the population, and we lose some of the details. So the question is, how do we design a good sample and avoid bias? So what are good samples look like? And one primary method to do that are observational studies. And matter of fact, most data is collected through observational studies. And basically an observational study is where we gather data about subjects doing what they are already doing. The research of historical records or medical records and surveys are all examples of observational data. Most data is collected through observational studies. So almost everything we do as far as sampling is through observational studies. And again, that's historical records, medical records, surveys, or observing people doing what they already do. It's a huge note. Observational studies do not assign treatments. And because treatments are not assigned, causation cannot be proved. However, observational studies can be statistically significant. So experiments assign treatments, observational studies do not. Because treatments are not assigned, causation cannot be proved using an observational study, but the results can be still statistically significant and demonstrate a relationship or an association. They just do not represent a causation. Only experiments should be used to establish cause and effect relationships. And again, most data is collected by observational study and not by controlled experiments due to time, ethics, etc. And we'll talk about that in another video later this week. So most common types of observational studies are the census, the convenience sample, the simple random sample, the systematic cluster, and stratified samples. And we're going to take a look at all of those in multiple videos. So the census, as we discussed earlier, involves the collection of data from each unit of the population. In other words, we surveyed everybody. We asked everybody their age. We asked everybody their eye color, or their height, or their weight, or all of the above. But as we discussed previously, it's often impossible, if not impractical, to perform. On the positive side, if we perform an accurate census, we'll have the population parameter of interest, and inference procedures will not be necessary. So if we can carry out a census, we don't really have need for statistics class because we know the actual measure of the population. We don't need to make generalizations about it. A lot of data is collected using the convenience sample. Unfortunately, convenience samples are very poor representatives of the sample and almost always biased. The convenience sample is a sampling technique which selects subjects because of their convenient accessibility and proximity to the researcher. We previously talked about surveying the 25 people at the lunch table. This would be a convenience sample. It was easy to do, easy to take. We didn't take a random sample, and it's rarely representative of the entire population. We said at the lunch table, the people you sat with probably had similar views and beliefs to you and might not represent everybody at Reagan High School. All right. And then, once again, if you have the biased data, then collecting it was worthless. So don't use convenience samples. So how do you avoid that? Well, the purpose, the most important thing is not to avoid, but to incorporate. The most important thing is to incorporate randomness. All right. And ideally, we want every group of our population to be proportionally represented in our sample. Unfortunately, we really break it down, we're all unique individuals. If you look around the classroom, there's not a single person like you. So it's impossible to perfectly represent the entire population without taking a census. And we discussed that that's already impractical, not going to happen. So we address this problem by the introduction of chance or randomness. All right. So we must, in our surveys, in our data collection, we need to introduce chance or randomness. And randomness or chance is the making it equally likely that any member of the population is chosen. And we have found, or statisticians and mathematicians have found, that randomness tends to equalize the variations that we can't account for in our studies. So when we actually involve randomness, we equalize the variations that we can't account for in our studies. I'll make sure I start that. Extremely important. All right, so let's do something without randomness. All right, so on the next page, we have a bunch of figures. And basically, I'd like you to, without thinking much about it, to go ahead and look at this page and select 5 figures that you think represent the population. So let's just say I circle this one, get a big one. That's 1, 2, 3, 4, and probably need another big one. All right, so those are the ones I circled. I hope they're representative. And I'm going to sit there and add them all up. So if I do that, 1, 2, 3, 4, 5, 6, 7, 8. And so I noticed that I chose number 62, and it had 8. I also chose number 65, and it had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I chose number 33. And it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it was 20. 74, that's the easy count. Thank you for that. That's number 2. And 75, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so 75 also was a 20. Now, I just rapidly sped through those and thought that they'd be pretty representative. Now, I recognize that we're in stats class, and you know that I have something up, but that's what I chose. And I divide by 5, and I find that the average size is 12. And that's really not surprising that I would get something that overrepresents it. Truthfully, if we added all these up, we should have gotten an average of about almost 8. 7.91 would have been the actual average. Now, I know that you couldn't have gotten 7.91 realistically choosing 5, but our class should average around those. But in general, we overrepresent large numbers when we do this. All right. So basically, just by eyeballing it, I ended up at 12. When I actually did this, just looking at it without writing anything down, the very first time I ever did this, I was way high. I ended up at 11. Okay. So how do I equalize that so I'm not using my judgment? Well, we could do the census, and I'm just going to tell you it took me a long time to do the census, which means I counted every single one of those up. I numbered them 1 to 100, and then I added them all up, and I got 791 squares. That was a pain. So let's look at a couple different types of samples that we could do. The first one is a simple random sample. And basically, it's a simple random sample. Every single individual has an equal chance of being selected, but also, very, very important, In a sample, random sample, all subjects have an equal chance of being selected, and every possible combination of subjects has an equal chance of being selected. In other words, it's equally likely that I would select 1, 2, 3, 4, and 5 as I would select 1, 12, 23, 43, and 44, or 53, 55, 54, 75, 77. Basically, every group has an equal chance of being selected. And essentially, a simple random sample is that I put everybody's name, or in this case, all these numbers into a hat and drew them and without replacement. And consequently, each one would have an equal chance of being selected. And each one would have an equal chance of being selected. And beyond that, each group of subjects has an equal chance of being selected. There is only one simple random sample, all right? Only one simple random sample. They're not multiple types. The only type of sample that says every possible combination has an equal chance is a simple random sample, all right? So simple random sample is kind of the starting point. And we're going to use our calculators to go ahead and create this. So here's what you do. We're going to go to Math, arrow over to PRB, which is probability. And we're going to scroll down to number 8, which should be random integer, no repeats. Random integer, no repeats, which is number 8. And all we did to get there was math, probability, random integer. Press enter. Then we're going to press a 1. Then there's a comma button right here. And we're going to press 100. All right. And then we can press enter. And basically we want square number 75 or number 77. So I'd find number 77. And then the next one was 65, 6, 33, 38. And I would count all those up and add them up. Well, then when I did it, I used a different set of numbers. And so to speed it up, I had number 10 or number 69, number 95, number 26, number 50, and number 58. And I ended up with an 11.4. Really not much better than my eyeball guess. But I'm betting that if I took the average of the averages, in other words, I averaged everyone in the class, we'd be pretty close to 7.9. So my point is, this simple random sample gives everybody the same chance. And I introduced randomness. I equalized the chance that I'd be selecting small ones and big ones, okay? All right, so the simple random sample is a really good place to start if you don't know anything about the population. The systematic random sample, on the other hand, we randomly choose the first number, all right? So and with a systematic random sample, every individual has an opportunity of being selected prior to us beginning our process. So everyone has an equal chance of being selected. Now, I wanted a sample size of 5, okay? Well, since I wanted a sample size of 5, I'll take my population size, which is 100. So my population was 100, and I'm going to divide it by 5. So I get 20. So now that is going to be 1 through 20 will be what I do with a random number generator. The first time I did a 1 through 100, but now I'm going to run it with 1 through 20. So when I did a 1 through 20, and I'll just show you how to do it real quickly. Math, probability, number 8, random integer, no repeats, 1, 20, and this time I got 14. Oops. Let me do that again. Math, probability, random integer, no repeats, 1, 20. And so this time I got 15. So my starting point would be 15. All right. After that, since we were going by 20s, it'd be, I would start off at 15, then 35, then 55. Now, when I did it, I got 19, 39, 59, 79, and 99. So basically, we randomly select the first number. Then every 20th number after that is chosen. Now, once again, we could have chosen any number 1 through 20, which means every single possibility 1 through 20 was possible, and every other number was possible as a result of that. But once we've started it, not every combination is available. For instance, once I chose 19, there was no way I could choose 20, or there was no way I could choose 18. Matter of fact, there was no way I could choose 38 because I was going by 20s. All right. So the simple random sample, the big thing is basically essentially putting everyone in the hat, and everybody has an equal chance, and every group has an equal chance. The systematic is going for the every nth one, right? It's the nth one that we're choosing. And in this case, it was the 20th. And how did we do that? We said we wanted a sample of 5. So we took the population size and divided it by the sample size. And that's where we started with our random number generator. The systematic sample is fairly rapid to do. It's great to do with a large population. It's great to use with people entering a stadium, etc. Very, very fast. And it's an easy way to accumulate data. We'll talk about other surveys in the next videos.